time for us to do some problems involving cross product. Well, that means we're going to do a little bit of practice with taking our little 3x3 determinants, making sure we check our work. It's really important because cross products are oftentimes the case because there's a little bit of computation where errors creep in. So get into the practice of checking your work. And of course, that comes with doing practice and practice. And so don't just watch the video, follow along and do the work. And make use of the pause button. Pause me and say, well, let me see if I can figure this out. And go and do the problem. And then let's compare answers. And pretty soon, you're going to be better than me, which is wonderful. That's what I want. So, all right, for now, let's begin. Our very first problem. Find a vector which is perpendicular to both 314 and 159. Of course, you might notice these numbers. 314, 159, digits of pi, right? Well, coincidence, sure, coincidence. I want to point out a key word here before we get started, which is this word, So when we talk about vectors which are perpendicular to two vectors, there's not a single answer. Notice it didn't say find the vector, but it says find a vector. Of course, we should expect there to be many possible vectors, because once we have a vector that's perpendicular to both, see, the key thing is it's a perpendicular vector. If you scale something, it doesn't change the direction. So it doesn't change whether or not it's perpendicular. So once we have an answer, we can find many more answers by appropriately scaling. Now, we could, of course, make things miserable on ourselves and do a lot of trial and error. We could also do things like, well, let's make a vector we want and take a vector dot 314, it has to be 0, and dot 159, it has to be 0, and two equations, and a couple of unknowns, we work our way through it. But that sounds like work. Our goal is to say, hey, let's find ways which are efficient. Now, whenever we're looking and we see, hey, I need to be perpendicular to both, something should cross your mind. The cross product. The cross product is our go-to tool whenever we're looking for something which is perpendicular to two given vectors. And we say, I know how to find the answer. So what we're going to do is we're going to take our vector 314 and we're going to take the cross product with 159. Now, you might be wondering, wait, how do we know it's the 314 that comes first? Shouldn't it be 159 cross 314? Does it matter? Well, at the end, if you did swap them, you would put a negative sign in. But that comes back to a scaling, which says it doesn't matter. If all we're after is perpendicular, it doesn't matter what order you take the cross product in. So any order is fine. So the way to do it, or at least the way I do it, is I say, all right, I, J, K are three vectors that point in our nice cardinal directions. 3, 1, 4, 1, 5, 9. Now I start going through the diagonals. And I can write the first diagonals over again. I actually like to do it just sort of wrapping around. So here we go, going downhill. I times 1 times 9. So I 1 times 9 would give us 9i. J times 4 times 1. See, J times 4, whoop, wrap around. Wrap around, see, J4, 1. 4J. K times 3 times 5. See, wrapping around. K, up. So that would be 15K. So downhill, add. Now, other direction, subtract. 1, 1K. So that's minus K, because we have to subtract it. I'm going to put that right underneath the other K. 5, 4, wrap around, I. 5 times 4 is 20, so that's 20i, but we subtract it. So subtract 20i. 9, wrap around, because 9, whoop, wrap around. 9 times 3, 27 times j. So minus 27j. Okay, now we'll just clean it up. We'll put it back into the component form here. So we say, all right, in the I slot, the first slot, 9 subtract 20. Negative 11. Okay. 4 subtract 27. Well, negative 23. 15 minus 1. See, there's no, if it's just minus k, it's like minus 1 times k. So 15 subtract 1, 14. And now we're done. We claim this is a vector. Well, it is a vector, and it has to be perpendicular to what we started with because that's the geometrical property of the cross product. Now, you might be a little bit, how are we sure we didn't make a mistake? This is something which I strongly encourage you to be a little paranoid about. And the way you check is you quickly do the dot products. So let's take 3, 1, 4, dot it with minus 11, minus 23, 14. And let's see what we get. Well, 3 times minus 11, minus 33. 1 times minus 23, minus 23. And then 4 times 14 is 56. And you see, this would be minus 56 plus 56 is 0. Good. And then you say, okay, check the other one. 1, 5, 9. Dot. Minus 11. Minus 23, 14. Well, minus 11. That's easy. 5 times negative 23. Well, that's negative 115. Now, in case you're wondering how do we get that, 5 times 20 is 100. And then 5 times 3 is 15, so you put them together. 9 times 14, well, that's 90. 9 times 10, plus another 36. 9 times 4. And so that would be, well, I lost track. So 90 plus 36 is a positive 126. Well, that's a negative 126. Plus 126 is 0. So good. So this is our check. So here, this is not part of the problem. This is our error checking. And if we had come over here and said, if this had been 5, we'd be like, and something went wrong. Now, it could be we made a mistake in our dot product, but more likely we made a mistake when we did our cross product. So that's the way we can go back and correct ourselves before we wreck ourselves, because it's really important that we do that. All right, good. So let's try another problem. So find the area of the triangle with the points 1, minus 1, minus 2, and minus 2, comma 0, minus 1, and 0, comma minus 2, comma 1 as vertices. So what do we have? Well, do we take the cross product? Probably. See, whenever we think of a problem and we see things like area, that oftentimes when we see an area, we think there's probably a cross product connection because there's this beautiful connection to areas of parallelograms and areas of triangles. And especially so area triangle, we think cross product. Now you might say, okay, start taking cross product, but we can't take cross product yet. These are points. They're not vectors. You can't take a cross product of points. You gotta find vectors to work with. So step 1 is let's make sure we don't rush into things and we know what we're doing. So we draw ourselves a picture. Now we don't need to be very precise here. We say, well, there's 3 points. So, all right, we draw ourselves 3 points. 1, minus 1, minus 2. Over here, minus 2, 0, minus 1. And over here, 0, minus 2, 1. And now we have the triangle. So we're after the area of that triangle. You'll notice I didn't pay attention to where the points were. I'm not worried about that. I'm worried about the intuition. We say to ourselves, the cross product is great at finding area if we can think about the vectors. We don't have vectors yet, so we need to get to where we have vectors. So that's going to be sort of the important step in this problem. How do we get the vectors that we need? Well, what we do is we create vectors, and there's actually a lot of choices here because there's lots of vectors you can make because you can go from this point to that point or that point to that point. You know, there's all sorts of vectors. And what I recommend is just pick a corner. Any corner will work. So I'll pick this corner. Nothing special about it. And I'm going to create the vectors that go to the other two corners. So when I look at the vector, I look at the change. So I say, okay, if I went from 0, -2, 1 to 1, -1, -2, I increased by 1 in the x-coordinate. I also increased by 1 in the y-coordinate. And 1 to -2 says I went down by 3 in the z-coordinate. So the vector is 1, 1, -3. That's this vector on the side. Here we say, okay, now what happened on this one? Well, we went down by 2 in the x-coordinate, so -2. -2 to 0 says you go up by 2, and then you have 1 to -1. That's a go down by 2. So down by 2, up by 2, down by 2. And there you go. So what happens here? Well, the next thing to do is we say, we know the area is going to be 1/2 the magnitude of the cross product of these two. So that's what we're going to find. We're going to figure out what's the cross product of these two vectors, the magnitude of that, and then multiply it by 1/2, and we're done. So the majority of the work now is going to be, what's the cross product? So here we go. I, j, k. 1, 1, -3, -2, +2, -2. And do your diagonals. I times 1 times -2, -2i. J times -3 times -2, +6j. K times 1 times 2, +2k. Now the other way. So we went downhill. Now we're going to go uphill. -2 times 1 times -k. Well, that's -2k, but we're going in the opposite direction, so we're going to subtract -2k, which will make it a +2k. I like to put the k's and j's and the i's over their respective other ones. 2 minus 3i, so that's -6i. Of course, we're subtracting -6i, so it's the same as adding 6i. And then -2, 1j, so that's -2j, but we're subtracting that, so it becomes +2j. So this looks like 4, 8, 4. 4, 8, 4. Now, what should we do? We should check. And the way we check is we do a quick dot product. So, for instance, what do we have? 4, 8, -12. 0. Phew. Okay, how about here? -8, 16, -8, 0. Good, good. We probably did something right. Well, of course, because we're careful. We're being methodical. We're not rushed. We're taking our time, enjoying the problem. All right, so now what? Well, the next thing is to say, what's the magnitude? Now, there's two choices. If I'm looking for the magnitude of the vector 4, 8, 4, one of the things I can do is just say, look, that's going to be the square root of 4 squared, 16, 8 squared, 64, 4 squared, another 16. Well, what's that? That's the square root of 96. And you might say, well, the square root of 96, can you simplify that? It turns out that 96 is it's divisible by 16. It's 16 times 6. And so if you take the square root of 16 out, that becomes 4 square root of 6. I said there was another thing you could do. Let's notice something. Everything here has a factor of 4. So let's pull out a 4. So in other words, I can think of this as the magnitude of 4 times 1, 2, 1. Well, now I can say, hey, the 4 really comes out. So that's 4 times the magnitude of 1, 2, 1. If this had been a negative number, when I take it out, I just take the positive of it. And now, that's an easy magnitude to compute. That's 4 square root of 1 plus 4 plus 1. Because 1 squared plus 2 squared plus 1 squared, which is 4 root 6. Same in either case. So we come back up here. Our answer is 1/2 of 4 root 6. Well, 1/2 goes into 4, so we end up with 2 square root of 6. And we're done. Now, before we run away from this problem, not that we need to run away from this problem, you might say, hey, you know, when I did this problem, Steve, I did something similar, but I chose a different corner, so I got some different intermediate steps. Did I do it right? And the answer is yes. In fact, there are several ways to do this problem, depending upon which corner you pick. And you're going to get the same answer. So there are sometimes multiple routes, but the destination should be the same, because the final answer is an area. It shouldn't depend upon how we do it. So it's okay if we did it slightly different ways. And again, you really can pick any corner. It doesn't matter. You just have to make sure you get 2 vectors so that vectors represent the sides of the triangles. And if you had swapped these two, well, that's just a difference of sign. When you take the magnitude, that goes away. So it's kind of forgiving in that way, which is nice. It's nice that, you know, it can take a little bit of, a little bit of variation, let's say. We'll put it that way. All right. Now, this problem. Very similar. Find the area of a triangle with vertices at 2, 1, 3, -2, and -1, -3. Now, we look at this problem and say, hey, perfect. This is going to be easy, right? Same thing, because we just did an area problem. Easy, right? Piece of cake. So we just mark our vertices. And again, I'm not going to worry about being precise. So, you know, you have a vertex over here. You have some vertex over here. You have some vertex over here. And you say, look, there's a triangle, and we should just use the cross product. But then you write, oh, wait a second. No, this is a 2-dimensional thing. Ah, no! Cross product it's so beautiful and elegant, and it works so great for finding areas of triangles, but it only works if we're in dimension 3. And this is dimension 2. No! Oh, we're... Oh, wait a second. Maybe there's a little thing we can do, though. Here's a fun fact. It turns out that dimension 2 is inside of dimension 3. Aha! So our tool, which only works for dimension 3, we can actually get it to work for dimension 2 as well by saying, hey, secretly, we can think of these as being the following. We can really think of these as being points -1, -3, 0. And 3, -2, 0. And as 2, 1, 0. Perfect. So there is sort of a little cheat. So you can use cross products in some sense in dimension 2. If you say, hey, dimension 2 fits into dimension 3, just imagine that the third coordinate is 0. Everything else is the same process. So we'll just run through it. We say, all right, we take this part right here. Well, that's what happened. If I went from 3, -2, 0 to 2, 1, 0, I went down by 1, and then I went up by 3, and then no change. So down by 1, up by 3, no change. Over here, what happens? Well, I went from 3 to -1, down by 4. I went from -2 to -3, down by 1. And whoops, I forgot to mark the third entry, no change. Remember, we're in 3 dimensions now. So now we repeat similar process. So we'll have -1, 3, 0, cross 4, -1, 0. Well, I, J, K, -1, 3, 0, 4, -1, 0. And we say, all right, now just work it through. I times 3 times 0. Gone. j times 0 times 4. Gone. K times minus 1 times minus 1 is K. Now, other direction. 4 times 3 times K. 12K, but we went in the other direction, so subtract. So subtract 12K. Now, negative 1 times 0 times I. Gone. 0 times negative 1 times j. Gone. So what we end up with is minus 11K, which is 0, 0, and minus 11. And we shouldn't be surprised that our vector really has this form, because our first two vectors were 0 in the last entry. Then the cross product will always have a form of 0, 0, something. And it's easy to see that they're automatically perpendicular. Another way to think about it is my current vectors are in the xy plane. The cross product has to be perpendicular to the xy plane, and therefore it should be some multiple of the vector k, which is what we see going on here. So our magnitude of our vector 0, 0, minus 11, well, that's going to be the square root of 0 plus minus 11 squared, which is going to become 11. It's easy to find the magnitude. So our final answer, we're after the area. So the area is half the magnitude. So we get 1/2 of the magnitude, which is 1/2 of 11, or if you like, 11 halves. And we're done. So that worked out rather nicely. So this is sort of a, hey, if you're in 2 dimensions, don't panic. You can still use your 3-dimensional tools, which is a nice thing to know. It's good to have more tools. The more you have, the farther you'll go. Hey guys, this is so sad. I thought I was doing great, but of course, even when you're doing great, the ideas are sound, but copy errors will still haunt us. Notice something. Whoops. Should have been a minus there. Well, how does that change things? Well, that makes that into a minus, which really makes this into a plus, because it'll be a plus 12k minus a minus 12k, which means this is 13. Well, that's not too bad because it makes it fairly easy to correct. And so our answer should be 13 over 2. So be careful. Be careful. No matter how good you are, it's easy to still make mistakes. Don't beat yourself up about making mistakes. You know, it's not like we're shooting to be perfect. What we're shooting to understand is to understand the processes. And that's the important part. So make sure you're doing a good job in understanding those processes. And just be good to yourself. Be kind. All right. Well, back to work. Let's keep going. One more problem. The volume of a tetrahedron is 1/6 of the volume of a parallelepiped, whose sides are formed using the vectors coming out of one corner of the tetrahedron. So let's see if we can do a quick sketch. And I'm always a little bit nervous when I try to draw a parallelepiped. So what happens here is you have a parallelepiped, so it's this shape coming up here. So you have all these parallel faces. And when we talk about the tetrahedron, what we mean is pick a corner, doesn't really matter, and you just think about the 3 edges coming out of that corner, and now form a little triangular face. So this is that tetrahedron. And it turns out, it's not so clear, but it's a true fact, that this piece here, this tetrahedron, is 1/6 of the total shape of that parallelepiped. So, now, what's our problem? Okay, find the volume of the tetrahedron with corners at 1, 1, 1, 1, 5, 5, 2, 1, 3, and 2, 2, 1. So this is really about a volume of a parallelepiped, and then we cut it by a factor of 1/6. Well, volumes are determinants. So we have the following fun fact. We start by marking our vertices, so it doesn't matter which one is which. I'll put this one in the corner. 1, 1, 1. We'll say this is 1, 5, 5. Up here, we'll say this is 2, 1, 3. And in the back, we'll put 2, 2, 1. So that's this little one in the back. What we need to do is say, I need to know the vectors that are coming out from the corner. So this corner, this is our special corner. I want to figure out the vectors that come from this corner to the other places. So from 1, 1, 1 to 1, 5, 5, that vector says don't change in the x, but change by 4 and 4 in the y. From 1, 1, 1 to 2, 1, 3, well, that says what? We change by 1 in x, nothing in y, and 2 in z. And the last one, 2, 2, 1, says we did the following. That's this little one here. We changed by 1, and then we didn't change at all. So, remember the formula for volume. Volumes for parallelepipeds are determinants. What you do is you pick a corner, you find the vectors coming out of that corner. Those vectors form the rows of a 3 by 3 matrix. So, we write down our 3 by 3 matrix. It doesn't matter which order we write it in. So I'll just pick an order. 1, 0, 2. 1, 1, 0, 0, 4, 4. And now we take the determinant. That number, once we take the determinant, make sure it's positive, is the volume of the whole parallelepiped. So, take the determinant. 1, 1, 4. Okay, that's 4. 2 times 1 times 4. That's 8 more. Then we have the 0, 0, 0. Okay, so 1, 1, 4, 0, 0, 0, 2, 1, 4. Now, that's going downhill, uphill. 0, 1, 2, 0. 4, 0, 1, 0. 4, 1, 0, 0. So, the determinant is 12, which means that the volume of the whole parallelepiped is 12. We only want the volume in the corner, which is 1, 6. So, the conclusion is our volume of our tetrahedron is going to be 1, 6 of 12, also known as 2. And that's our answer. A nice answer, beautiful answer. And this gets back to thinking, it's like, hey, we can think of volumes. We can find volumes. We can also find areas. There's lots of geometrical things now we can do with these operations. Now you might say, where was the cross product involved? Well, the cross product is sort of hidden now in the machinery. We use the cross product to find this formula that says, hey, when we take a determinant, that's a volume. But it's still there. It's still in our machinery. All right, good. Well, that was some good practice. Probably we should do some more. And of course, we should always keep practicing. As we practice, we keep getting better. All right. Have a great day.